YouTube, LinkedIn, Twitch, Twitter, Facebook, YouTube. I think I heard, did I say YouTube? Hello there, everybody. This is
Hello,
OpenCV
everybody.
Live. I hope you enjoyed the break. Don't expect it to happen again. And we're live everywhere. So as you join us, please tell us where you're joining us from. We love to see the OpenCV community chime in the comments wherever you're watching on the wide world of Al Gore's internet. I am, of course, coming to you from beautiful downtown San Francisco, California, the fragrant Soma neighborhood. And our stalwart host, Dr. Satya Mallick, is coming to us from
San Diego, yet again.
good old San Diego.
The weather
Hello,
has been
wow.
really nice for the last few days after the rains.
Yeah, the rain, the weather's been interesting here in San Francisco. It's alternating between some of the nicest days we've had in a long time and
The
kind of
crappiest.
really foggy rain, you know?
Yeah.
Hello, France. Hello, Brazil. Hello, Nigeria, Portugal. More France, Brazil, Romania. From awesome Nigeria, Switzerland, Cyprus, Mexico, Canada, Bolivia, India, Chicago, Iran, Ghana,
Wow.
Poland.
We have quite
Another
a crowd.
yes, another downtown San Franciscoite. Hello, Irvine, California, Kashmir. Great Led Zeppelin song. Yeah, there's 20 of you folks watching on YouTube right now. I'm not sure. Let's take a look at the numbers on LinkedIn. 97 strong on LinkedIn. We love to see it, folks. We just passed, I think, 16,000 subscribers on YouTube, which is a big number for us. Thanks to everybody and
Because we just
all you.
started. I mean,
Yeah,
even though we
yeah.
have been doing this for a while, we had not started our YouTube channel. We were using OpenCV.ai YouTube channel to host these, but now we have a separate OpenCV Live YouTube channel.
That's right, and we've actually eclipsed the subscriber count on that old channel by like twice over now, so
All
super
right.
awesome. Hello, Mumbai, Atlanta, Georgia, New Mexico, Ethiopia, Santa Cruz, Switzerland, Treaty 6 territory in Canada, Philly, uh,
Wow.
Mountain View,
That's a
California,
big
Ghana.
crowd showing up today. We are nearly 100. We'll just wait for another minute or so
Yeah,
before we start. Um,
yeah. Just
and
give us a
please
second to let
introduce
the
yourself.
flop sweat dry a little bit. Yeah.
Right. We are more than 100 on Zoom. We are about 100 on LinkedIn, I think, and a few on YouTube. Great.
Yeah, 27 on YouTube. It's over. We have about 225 of you watching right now.
All right. And today we are going to have a very exciting session. We decided to do a tutorial, which we have not done in a while. And we are going to cover gaze tracking. If you don't know anything about gaze tracking, this is the right tutorial for you. Uh, so I think we can get started now, right?
Yeah, go for it, boss.
Hello, everybody. This is OpenCV Live. I'm your host, Satya Mallick, CEO of OpenCV.org. And today we are going to cover the topic of gaze tracking, which has become very common now with Apple Vision Pro and Meta Quest, Quest and Quest Pro, which have gaze tracking so that you can control the screen or the virtual screen on using your eyes, right? And as always, with me is Phil Nelson, who is the Director of Content and Creative at OpenCV. Phil organizes this show, and if anything goes wrong, it's his fault.
That's right. If anything goes wrong, it's usually my fault. I am your co-host with the co-most, the second banana who is second to none. I'm also your plus one and only. It's Mr. Nelson if you're nasty, but my dear friends here on OpenCV Live can call me Phil. And I'm here to remind you of a few things we do on every single episode of this show. This is 123 if you're counting out there. One of the things we do on this show is a giveaway to you in the audience. Stay tuned. Later in the episode, I will be asking a trivia question I make up during the show, and the first person to answer that question in the Zoom chat will win the OpenCV course of their choosing. Now, we launched OpenCV University at CVPR last year, and it's been very successful and popular so far. we love giving away these courses to people that need them to help them in their careers, and they can go out and tell people how useful the courses were, and then, maybe those people go buy a course. So even if you don't win today, go check out what courses are available at opencv.org/university. If you're not in the Zoom chat, which I must remind you is the only way to win a course today, you can get there by going to opencv.live. That's opencv.live. We are also taking questions from you in the audience. Use the Zoom Q&A button at the bottom of the screen, or type your question into the chat system wherever you're watching. We're live on YouTube, LinkedIn, Twitch, Twitter, Facebook, and probably some others that we don't even know about. Hopefully, if we're popular enough, somebody is pirating this stream. Back to you, Satya.
Thank you. Yeah, so I'll talk about gaze tracking, and I just bought this Apple Vision Pro. You can see here, and I've
Ooh,
been using it.
la-di-da.
Yeah, looks glassy and expensive because it is glassy and expensive. So
Sometimes you can judge a book by its cover.
that's true. And one of the things I realized is that these devices have extremely good gaze tracking now. Like when you use it, you feel that you're living in the future, right? You can actually the way Apple Vision Pro works is you put on this display and you see your room. Inside your room, you see some objects, right? You could be looking at a collection of icons to for applications, right? And the way it works is that you look at the icon inside this virtual environment. You just stare at it, and then you pinch your fingers, right? You tap your finger like that, and that is the selection and tapping. So you select icons using your gaze. For that kind of application, the gaze needs to be extremely, extremely accurate, right? And you can also type using your gaze. They show up show a keyboard, and you look at a particular character, and then you do tap, and it selects that character, and you can tap. It's not very efficient, but this is also the way gaze tracking was invented, because people who did not have good use of their hands, or did not have hands, they could use the computer without actually using their hands. So that is how gaze tracking used to work, right? You could just stare at it. Yep.
I've got a quick drop in here, which some people know, and some people watching, in fact, may have worked there with me. But I worked at a company called Occipital for many years, and we worked on an early iPhone-based headset called Bridge. I actually designed the logo and did a bunch of other stuff. Thanks so much to my friend Jesse for collaborating with me on that. But that was, we actually were using the term spatial computing back then to describe what we were doing. And in fact, almost all of the experiences with Bridge headset worked very similarly to how Apple Vision Pro works, which is we would do a quick sort of capture of the space to help with positional tracking and blah blah, even if you weren't going to be using the space. Right. And then you could use that space for games, or to put up a screen or a video, or even teleconference with someone in a different space and see their space through your headset. And so it's super gratifying, like 7 years later, to see that, like, okay, we were on the right track. We were just a little bit too early.
Yeah.
So, and but some of that team, in fact, went to Apple to work on the Apple Vision Pro. So,
right.
Yeah, shout out to John Amir, Pat, Forrest. I think there's a few others out there, but I hope you're all well. It's been a while.
Yeah, it's amazing technology. So let's dive into what is inside, how it works. Even the definition, some people may not. I mean, when I first started, I had many different views, understanding of gaze tracking. So let's start. Okay, so hopefully people are able to see my screen. Please let me know. Yes?
Looks great.
In the chat? Okay, great. So gaze tracking, just before we start, I just want to give a quick introduction for people who may not be familiar. My name is Satya Mallick. I have a short career in terms of the number of companies I have worked with. In 2007, right out of my PhD, I started a company called Site Commerce Inc., also called TAS. It was a computer vision, and it was a computer vision company for the beauty and fashion industry. Women could upload a picture and apply makeup virtually. And this was a pretty big hit at that time. But We had, Oprah magazine covered us, and we were InStyle magazine, People magazine. All these people were our clients. So technically, it was doing very well. And this was back in 2006, 2007, Adobe Flash technology. But still, people had a lot of fun with the technique. But as I have mentioned several times, commercially, this was a super duper flop for me. I made $0 million from this company, but great learning experience, as they say.
Yeah, if I had $1 million for every time I made $0 million, boy howdy.
Oh. In 2014, I decided to start Big Vision LLC. This is a computer vision and a machine learning consulting company, and we are celebrating our 10-year anniversary this year. In fact, in February 3rd, we turned 10 years old, and it's a big achievement for us because
That
initially.
was 2 days after I turned 41 years old.
Oh,
So
wow!
yeah,
Congratulations.
yeah, congratulations to Big Vision. Hokey smokes.
Yeah, and this company I started without any external funding. Initially, it was just to do my consulting work, but now we are about 80 people or so, and part of it is the course business, and the other is the consulting business. And then I became the CEO of OpenCV.org in 2019, and now I have these dual roles: CEO of OpenCV.org, which is my charity work, right? Because I don't get this is not what makes money for me or anything. This is something that I really love doing, serving the community. And Big Vision is the one that pays the bills, right?
Yeah, you and me both, boss.
All right. So Big Vision, I'm not going to go deep into the company or anything like that, but it is a computer vision and AI consulting services company. If you have a project that needs help with computer vision, please reach out to us, bigvision.ai, contacts at bigvision.ai. And to check out some case studies, you can go and check out this link that I've shared here. And that's all about Big Vision. Now we'll deep dive into the main topic. Okay. So the talk outline, I have divided the talk into 4 parts. First of all, I'll cover the problem statement. What is gaze tracking? Secondly, we'll go over how is the ground truth for gaze tracking covered, right? So when you want to create any neural network model or any AI model, the very first thing is that you have to collect data and generate the ground truth. And then you can use that data to train a model. And it is not obvious, right? How do you even collect the data for gaze tracking? So we'll cover that. Then we'll go over some data sets that are available publicly, and then we'll talk about gaze tracking algorithms, right? So it covers a very broad range of things, and you don't need to have any understanding of any computer vision techniques or anything to understand this talk. At the same time, this talk is not, I'm not going to go over programming of it. I'll just talk about broad concepts so that you get an idea of where things are.
And a quick note for the folks that have just joined us, we are taking questions from the audience. If you have them during any point in the show, feel free to use the Zoom questions and answers button, or just type them into the chat system wherever you're watching, and I'll do my best to make sure we surface those during the talk.
Great. So gaze trackers, there are 2 kinds of gaze trackers, and now there are 3 kinds of gaze trackers, which is a combination of the 2. But let's go over the 2 basic ones, and then, Apple Vision Pro and MetaQuest, they combine the 2 into 1. So one is the screen-based gaze trackers. And the idea here is that you're looking at a screen, and you want to find the direction on the screen where exactly you're looking. And this was very much applications oriented, right? Marketeers and others, they wanted to know, looking at a website, what are your hotspots? Where are you focusing on, right? Or looking at a product catalog, how is the catalog laid so that where are you looking at, right? So those kinds of things where the object you're looking at is a plane, and you want to find where the eyes are looking at on this plane, right? It is a plane. The second, so basically you want the XY location on the screen. The second one is a variable screen, right? Now here also the tracking is on an image plane. So you can look at this thing called the screen camera on this wearable device. You're looking one from Pupil Labs and other by Tobii. Tobii has many different kinds of wearable devices, and they are probably the leading manufacturers in this kind of wearable eye trackers. So here,
They also look the most like the Borg from Star Trek.
that's true. Um, so what you're looking at here, there are two cameras. One is called the screen camera. So this is capturing what you're approximately looking at, because it is roughly at the center of the two eyes. And then there are other cameras which are tracking your eyelids, right? So you can see that essentially you're tracking the gaze on screens, right? Either it is an image that you have acquired using this scene camera, or you're directly looking at the screen, right? So it's a plane that you want to find the gaze on. And you also have an eye tracking camera, right? So you have a camera here. You can see, you cannot see in this image, but right here, these things that are sticking out, they have cameras. And in this system, you have the camera right here, right? And these cameras are really not, a single camera usually. They are multiple cameras, but at the very least, they consist of a camera and an IR LED, right? So this is not a single camera. Here you will have a camera and an LED. And the LED is used to illuminate the eye, because you could be looking at in very dark environments. And these things are IR, which means infrared, because the human eye cannot perceive infrared. So you're projecting something onto the eye, but you cannot see it, right? But the camera can see it. The cameras are IR cameras. They are sensitive to IR rays. So they can see everything, but your vision is not obstructed, or you are not feeling uncomfortable because these are IR rays, right? So that's the setup for these IR cameras. Now, what does the image look like? If you take a picture using these cameras, the image looks something like this. What you're looking at, you can see that you have the image, and it looks grayscale, right? It is really in the IR domain. It is it is beyond the visible spectrum, but it still looks like a grayscale image, which is great. And you also see that light on the pupil, not the pupil, this is coming off of the cornea, which is a part of the eye that is covering the pupil. And so here you can see the reflection of the IR LED, right? And so these are typical images. This is not a typical image. This is about the best quality image you can get. But you get an idea what kind of image you capture, okay? So the gaze estimation problem is reduced to this. You have two cameras, right? Or two screens. So the first screen is this, right? Or this is an image or a screen, whatever it is. And you have this image that you have captured using the IR camera. You need to figure out, using this, right? Using this image on the left alone, right? That's the only input you have. What point, what XY location in this image you're looking at. So it's a two camera system. You have two images. The image on the left, you need to use to find which point on the image on the right is the person looking at, right? So that is the gaze estimation problem, right? Very simple once you set it up in this way. And the same thing holds true for your displays also, right? If you have a head-mounted display, they are taking pictures of your eyes, and you need to find inside this display screen where exactly we are looking, okay? And the same happens with this different setup also. You have a screen, you have this camera and IR LED located here. You take a picture. From this, you need to estimate where exactly is the person gazing at, right? They could be looking at this point. So that's the gaze estimation problem.
Interesting note from YouTube. Another benefit of infrared and why it's useful for this is that Unlike visible light, infrared will not cause your pupils to constrict.
Okay. I mean, that makes sense. That makes sense.
Hadn't thought of that. Yeah.
Yeah, I had not thought about that, but that now makes sense.
Shout out to Gabriel and YouTube for that one.
All right. Okay, so in Apple Vision Pro, where are these things located? I actually started, when I got this, one of the very first things I did was I started counting the cameras. There are 12 cameras, of which I could find only 8, because these IR cameras are located inside. I've tried to shine light into it and try to figure out, but they are not visible, at least not to me, through these. But I got this from the URL that I am showing. And I think Apple may have released this thing at some point last year. So you can see that there are 2 IR cameras, not just one, but per eye. And so there are 4 IR cameras. So out of the 12 cameras, 4 cameras are dedicated for just eye tracking. That's how important the problem is, right? And you can see that there are these LED lights all over, surrounding that. And so you'll see several LED lights, not just one, that illuminates the eye. And that is why, all these things, extra cameras, extra lights, they all make sure that the quality is really good, right? Now, okay. So you can imagine, right? Apple Vision Pro is both wearable, but it also has a screen. So it's a combination of the two. It is actually, if you think about it, is much closer to the screen system than the wearable system, right? Because we are not looking at a camera view of the outside. But it's actually a combination of both those systems. Now, Tobii Vision Pro also looks very, interesting. So these are glasses that you can use. And if you're looking at the real world, let's say you're reading a newspaper, you can use these glasses to see where the person was looking at. And these are used by all kinds of research agencies who want to see, let's say you're walking down a shopping aisle, looking at different products, what products, grab your attention, what is the person looking at? So they would, they'll put these people in the field to just go around shopping malls. They will, or even if you're doing marketing, they would look at pamphlets, etc., to see where people's gaze is going, what is drawing their attention, etc. And here also you can see that the system consists of one scene camera, as I had mentioned. There are 2 cameras for, these cameras are looking inward into your eye, but you can see that there are 2 cameras per eye that are looking into your eye for gaze tracking. And these other things, which are not marked in blue, these other things are LED lights that illuminate the eye. So the lights are also very, very important. And you can see that people use multiple of those. So you can go to this and see a demo of this, how it works. Pretty fascinating device. And you can record this on your computer. So the question is, how do you even get ground truth for training such a system, right? The easy answer is that, you have a screen, right? And you ask people to fixate at a point, right? You say that, okay, we know the location of this point. You could be showing them a target, a pulsating target sometimes, so that their attention is going to that, and ask them to focus there for a second or so. And then you know that, okay, this person was looking at that location. And so you have the ground truth, and you also have the picture of their eye taken at the same time, right? So this is called active, when you're saying that, oh, look at the screen. This kind of data generation is called active. The other kind is called passive, right? Where you ask the person to wear some glasses, but just do their work normally, right? They are not actually following any instructions. They say that just wear these glasses and use the computer as you would in normal day-to-day work. And there are certain activities that require you to look very closely. Reading is not one of them. If you're reading something, you're not actually focusing on individual words even sometimes, because it is pattern recognition. You go very fast and you're not reading. If you are typing, etc., are also not there. But let's say you are clicking on a button, then your attention goes to that button, you make a click. Double clicking is another example where people pay very specific attention. The gaze is focused while double clicking, right? So knowing when people double clicked, when they clicked on a button, etc. And if, in a normal course, you can imagine that these things are happening all over the screen. So you can gather that data passively without requiring people to pay specific attention, right? So now let's go over to some algorithmic thing. One of the prime things, right? We will go into how exactly gaze estimation is done, but one of the core algorithms in gaze estimation is pupil detection, okay? So pupil detection is, there are two different configurations of camera and lights that people normally use for pupil detection. One is called the dark pupil, right? In dark pupil, you have the camera and you have the light source, and you take a picture that looks about like this, right? And then the pupil is dark here, and you can easily detect the pupil because you can see how high contrast the image is. The other approach is to use to co-locate the light and the camera. And when that happens, you can, people who are old enough where we had cameras that produce these red eyes, may remember, right? It
Yes.
was a very common problem whenever you did flash photography, but the person was looking straight into the camera, they would see these red eyes, ghost-like red eyes. And
Yes,
in
there was
bright,
even it was even a big feature for cameras at one point to have red eye reduction, if you can believe
yes,
that.
yes. In fact, I have a blog post about red eye reduction,
Yeah, you have
automatic
been
red eye
doing this a long
reduction.
time.
Right. So yeah, and so the same concept is used here for bright pupil. So when the camera and the light source, they are co-located, then it produces a bright pupil. And you can use slightly different algorithms for locating this bright pupil as well. Now, the camera configuration, right? You cannot, I just made up this configuration, but you cannot actually use a camera right there because usually the person wants to see something other than the camera, right? The goal is not to track the eyes. The goal is for the person to look at something, and the camera should not get in the way. In this configuration, obviously, the camera is getting in the way. So obviously, you cannot put the cameras right in front. And when you put the camera on the side, the quality of the image just degrades, right, substantially. You can see that, first of all, it is no longer a circle. The pupil and the eyeball itself, they are no longer circles. And so that adds some amount of complexity. But so it's, that's one configuration. But you can make the configuration better by using a beam splitter, right? And this, there are systems that work on this kind of images as well, but you could alternatively use a beam splitter where it is a half silvered mirror. The eye is looking through this half silvered mirror, and you are actually getting a reflection of the eye in the camera, but you can also see outside, right? It's almost like you're working in a slightly darker room, 50% darker room than normally you would. You can still see fine. The pupils will dilate better, right? And this is a setup you can use to get higher quality images. Now, I tried to figure out, what does Apple Vision Pro use? What kind of configuration it uses? And I very stupidly went and checked out their patent. So one of the configurations in the patent is this one, where you can see that the camera is looking at an angle, and these little things, 130, those are LED lights, and then they have this lens or mirror kind of thing, and then you have the screen that it is looking at. Okay, so I said, okay, that's a simple configuration. But then it also mentions this configuration where this thing that you're looking at is actually a hot mirror, right? It reflects light. So you have this configuration in which you're using a beam splitter kind of thing, right? But and then finally you have a physical beam splitter as well, which is placed behind the lens, which made me realize that patterns are the worst things to understand how things actually work, because here they are trying to cover all the various things that somebody could utilize instead of telling us how they actually did it, right? But it's good to know that it is, one of these three configurations they might have used. It's very difficult for me to confirm which one it is. But over time, people will take these things apart, and we will know more about what exact configuration is used.
These patent drawings are they remind me of Salvador Dali. Like I'm thinking of Un Chien Andalou, like yeah, or possibly A Clockwork Orange.
Right. Okay. So the pupil detection, even though I showed very nice images, etc., and I said that, oh, you can use circle detection, etc. But in reality, this is very, very challenging, right? If you look at these real images, you have problems with viewpoint when the camera is not looking straight. People could be wearing glasses. You could have partially closed, eyes. There is natural
You
eyes also
you
have
you might be a
variations.
little bit stoned.
Oh, that's true. That's true. Yes. And then the
Not that
lighting.
I'd know anything about that, obviously.
Of course not. Of course not. How would you possibly?
I'm a good boy.
Yeah. So no comments on that. So yeah, so these are the various challenges, right? And this YouTube link has more details on challenges, some real videos, etc., where you see how challenging even a simple task as circle detection, right? In the real world, simple things that look very simple in when you're solving a toy problem, when they have to be solved with a very high level of accuracy under different conditions, they become very, very challenging, right? So the algorithms until recently, when I say recently, until like say 5 years back, most of the algorithms used very traditional computer vision techniques. They used edge detection, ellipse fitting, low-level vision, the same kinds of techniques that you would use in a class project. They were actually used in the final product also. And the accuracy was not great. But starting, let's say more than 5 years back, CNNs, deep neural networks, they took over. And now most of the systems are based on neural networks. And we'll learn a little bit about them as well. So before we dive into this thing, right, let me explain a little bit about the eye model, right? So this is, I just created a schematic diagram of the eye. Obviously, things are not so circular and spherical and pure, but the screen on which the eye projects uh, the image that it looks at is called the retina. In front of the retina, we have this lens, which basically tries to focus everything onto the retina. And then we have these almost muscles, you can say, called iris, which controls how much light how much light gets into the eye. And that opening is called the pupil, right? On top of the pupil, we have a layer called cornea. This is a transparent layer, and this basically protects the eye. So you may think, right, that this is the direction of gaze. Here, what I have done is I have connected the center of the pupil right here to the center of the lens and drawn a line, right? You would think that this optical axis is actually the gaze direction. It turns out that there is another part of the eye called the fovea. It is off center. It is not exactly where it is located, right, along the optical axis. And fovea is where you get the sharpest image, right? The lens construction inside the eye is such that it is not along this axis, along the optical axis, but slightly off. And this is actually the gaze direction. The gaze direction is given by this line that connects the center of this fovea to the center of the pupil, right? So that is the visual axis, that is the gaze. And we have the optical axis, which is slightly different. And this angle is called kappa, or sometimes there's another word for it. I can't remember, maybe it's called alpha or something like that. But this angle is very specific to humans, individuals. So this is not same. My kappa angle would be very different from yours. So this needs to be estimated, and it cannot be estimated using and using images directly, right?
That's
So you
interesting.
have,
Is that unique enough to be used for identification, would you say?
I don't think so, because there is an overlap, right? They all lie between, let's say, they are approximately 5 degrees, right?
There's a spectrum you're saying on the, yeah.
Yeah, but it's not unique, right? So two people can have the same angle. It's not unique, right? But they are not the same, right? It may differ. It's approximately 5 degrees. So for good high quality eye tracking, you need user specific calibration, and that is why when you actually use the Apple Vision Pro for the first time, you will have to go through this calibration step where they ask you to look at there are circles in a circle. The circles arranged in a circle, and they say that gaze here, look at that, look at that, look at that, and so on and so forth, right? So that you're able to they know this angle. They are trying to find what this angle is. However, that said, it turns out that their eye tracking is pretty good. Even so, I calibrated the system for my eyes, but my friends have used it, and they were able to do eye tracking based, user interface. They were able to use it just fine. But obviously, it is much better for my eyes when I do it. Maybe the accuracy is much better. But it is a fact that you need to do user-based camera calibration. There is no getting around that. There is no image-based method that is possible to solve this problem. Okay, and to do this, what people do is, they first put some dots on the screen, and in a calibrated setup, they also figure out where the person is gazing using the algorithms that they develop. They figure out, what is the gaze direction and where where they had actually pointed and where they actually looked, and this distance it gives you, an estimate of kappa. Um, there is something more also, so I just mentioned that people use pupil, right? What other features? Pupil is not enough to tell you, even if you locate the pupil very accurately, it is not enough to tell you where the person is looking, because, pupil, if you think about it, it is basically 1 degree of freedom, right? There is a circle and the center of the circle, but you need more information because the person is looking, in 3D. So the other information people use is the light reflected off of the cornea, right? So you can imagine this is the cornea. It is a transparent film on top of the pupil. And if you shine a light on it, some of it would reflect back and enter the camera. And we have already seen, right? You have the pupil here, and this is the reflection of the light on the pupil. So you have 2 points, right? If you can locate them, you get more information about where the gaze is tracked, right? So this is light detection, and you also have pupil detection. And based on that, you can these 2 things. You find this line which connect the center of the pupil to this corneal reflection, and there are a whole bunch of algorithms that use this information to estimate where the person is gazing, right? And if you want to learn more about this thing, just search for pupil center corneal reflection, PCCR, and you will see how this thing is used, right? So, but the thing is that there is no reason for just using these 2 features, right? You can actually use many features on the eye to estimate where the eye is looking together. So some of these features may not be useful, and if the machine learning algorithm is doing its job, those features would just drop out. But using more information is always a good idea, right? Because if you're using the right machine learning algorithm, some of the information will be automatically removed. They will not be used if it is not useful. So you can see here, you can track all these points on the boundary of the eyes. You can track the corneal reflection location, the iris location, and the pupil location to estimate where the person is looking. So now the gaze estimation becomes, you have this image. On these images, on the eye image, you detect all these features. From those features, you estimate the gaze, right? So that's how the gaze mapping works. Now, you may be thinking, okay, and the same thing applies to this other setup as well. So how is this, feature-based methods, how do they work? There are two ways of doing this. One is to have a geometric representation of the eye, right? And sometimes this geometric representation includes head and the eyeball. And there are other methods that also use RGBD cameras. And the main important thing is that they have a 3D model of the eye in between, as an in-between, right? From these features, they estimate the parameters of this 3D model. And from that 3D model, they are able to estimate where the person is gazing, because it's a 3D. Just imagine that they have a 3D eye looking, right? And they can just connect the fovea to the center of the lens. Once the parameters have been accurately estimated, and you find the location. This requires sophisticated modeling, right, of the eye. And you can imagine modeling the eyeball and the cornea as spheres, the pupil and iris as concentric circles. But you can have very sophisticated models. There is no end to it, to physically make it as close to the human eye as possible. And you need to know enough biology and how the human eye works to make these models. But plenty of companies have used this approach, especially when the requirement is very stringent, right? When you want very high level accuracy, then they go for this intermediate 3D model representation and then estimate the gaze. But the newer methods, which are much faster, they go from features to the gaze directly, right? This is basically 2D regression. You can imagine that all these feature points, you can string them as a vector. So this is a vector that represents the eye. From this vector, how do you find the XY location? And it becomes a regression problem. And you may think that, oh, how does it work without the intermediate 3D representation? Think about it as an implicit way, right? When computer vision started, right, and you had a robotic manipulation problem. So everybody thought that, let's say you want to lift a pen, the robot hand has to lift a pen from a table. At that time, the thinking was that you need a 3D model of the hand, you need the 3D model of the pen, and only then will you be able to lift it properly, right? And this was proven to be false. This was proven to be false because now machine learning algorithms, if you have enough images showing how the person goes and lifts the pen, you will be able to train a robot to go and lift the pen, right? There is no intermediate 3D representation. It is directly from the images. So the robot looks at the image just like humans look at the pen. You can lift a pen even with a single eye, right? You don't need depth estimation. So because you have prior knowledge of what this thing looks like, and you'll be able to grab a pen. The same thing applies here. You don't need a 3D representation always, right? You can train if you have enough data. Earlier, we did not have enough data, and that is why it was super important to have a 3D model which had this parametric model that you could train. But now, if you have enough data, who cares about the intermediate representation? Just go directly solve a regression problem because you have enough data. Another thing, when you look at the literature for eye estimation, gaze estimation, you will find something called cross ratio based methods. This is I really like this method because it's so simple and it solves the problem in a very elegant way, a very easy way, right? When the situation is right. And this happens when you're looking at a screen, right? If you're looking at the screen, you can put 4 lights on the end, on the 4 corners of the screen, right? Now, these 4 corners, right, these 4 lights would reflect in the eye, as you can see in this picture, okay? And you can detect, because these are lights, you can easily detect the location. And then you take another camera, which is co-located with the light, and you get this bright pupil, and you can easily detect the pupil, right? Now, see how easily they have used the geometry. Here is what the geometry looks like. You have detected the pupil, and you have detected the 4 points. These 4 points correspond to these 4 points. And assuming that the cornea is approximately planar, or you could even model the cornea, but for simplicity, just assume if the this thing is planar. In that case, you could find what is the center of this point and just map it. It is basically a mapping from one plane to another plane, right? It's a homography. So any point, you find the homography using these 4 points, and then you can map any point, which is the center of this thing, and map to the screen, right? And you have to do user-specific calibration to find out what is the kappa angle, and you're done. So very simple setup to get very high accuracy output. And it's very simple. So it's used when the situation allows it, right? When you have a setup where you can put these lights on the side of the screen, then you can use this method. Another method is based on appearance. So there is this class of there's something called 3D morphable models. 3D morphable models are models of, let's say, the human head, where you can morph, you can change. They are called morphable models because there are parameters. Just imagine there are knobs that you can change. And based on the setting of the knob, the head size may change, the nose shape may change. Different things can change based on, based on what is the knob setting, right? And these models have been created by using many 3D scans of human heads and eyes, etc., right? So you get this 3D model. Now, the goal here is that using this 3D model, you have a picture of the eye, and you try to morph the model, the 3D morphable model, so that your model looks as close to your picture as possible. And once you have done that, because it's a 3D morphable model, you know all the information. It's a synthetic thing, right? You know all the information in this 3D model about gaze direction, everything. So now, because you have mapped, you have changed the parameters based on the appearance of the image, you can find the gaze directly, right? Because in the 3D morphable model, you have gaze information embedded inside it. So that's, but as you can imagine, that this is a much more expensive operation to first generate the appearance to be as close to the image you're looking at, and then find it. It's typically anything that involves 3D morphable models. They're difficult to make it.
Yeah.
They're computationally expensive. Yeah. In fact, facial feature detection, we used to do it back in 2006 when I started our company, where we did face beautification and applying makeup on face. We had to automatically determine the location of lips, eyes, mouth, etc. And there we used a 3D morphable model in the backend. And it used to take, I cannot remember, 8 to 10 seconds. And we were thrilled that how fast it was, right?
Again, how times change.
Right. And now those things can be done in real time with much higher accuracy. Not even real time. Facial landmark detection works 1,000 frames a second, right? So it can be that fast. So a comparison of gaze tracking estimation techniques. I'm not going to go into all the details, but in general, this was true a few years back. This might be changing now. 3D model-based techniques used to have higher accuracy. You can see that the gaze estimation accuracy is less than 1%. And all these other methods, regression-based methods, etc., had 1 to 2 degrees accuracy. But I'm pretty certain that this thing is changing now, and because we have a lot more data to solve these problems. So let me just take a little break to understand, are people getting this, what I'm teaching? Is that I mean, the goal is not to go into, deep technical detail about each algorithm, but get a rough overview of various techniques out there. Yes? Give me a
Yeah, it
yes in the
seems.
chat. All
Yeah,
right, all right.
people are following, and we've had some good comments about like Abra in the chat's been talking a bit about how Cadillac and BMW use similar methods as these to detect driver alertness and maybe wake people up if they've been behind the wheel a little bit too long, stuff like that.
That's great. And we have 172 on Zoom alone.
Yep,
People,
we've
and I'm
we've been
guessing that
over
LinkedIn.
yeah over 300 concurrent viewers this whole show so far.
All right, good. Yeah, motivates me a lot. So let's look at the recent trends in gaze estimation. The biggest trend is synthetic data. People realize that, if you don't have synthetic data, you have to create these intermediate models, etc. But now the techniques have grown to a level that you can create synthetic data. So in 2015, a data set called Synthesis Eyes was published. It created, they used high quality 3D scans. The annotation became automatic, and they did this very photorealistic rendering of the eye. So these were 3D models, and from that you could render the eyes. And you can imagine that you can change the material properties of the eyes. It could be a blue eye, it could be a red eye, not red eye, brown eyes, or, or other kinds of colors, hazel eyes, black eyes, without actually changing anything, right? You have the geometry, you have, yeah, go
You were
ahead.
joking there, but somebody just asked, how would contact lenses affect this, for example? You can get those color change contacts or like monster eyes. Like how would that totally trash this sort of thing? Or
No. It works just fine. Contact lenses, because they are transparent, right? And through that, you can still see what the location of the pupil is. So it doesn't affect.
so they may have red eyes.
Right, that's true. Around Halloween. So Synthes eyes, they created, I mean, at that time in 2015, this was a very large data set of 11,382 synthetic RGB images. And they also had change in head pose, a 40-degree variation in head pose and 90-degree variation in gaze. And you can look at these images, some of them look kind of fake, but most of them look pretty realistic, right? And especially if you you can see the eye shapes, etc., you get a very, very high variety in the different shapes of eyes, etc., because these were based on real scans, right?
And
So
also, this looks extremely Salvador Dali. Like I can't. This you could have pulled this right out of an art history book on surrealism.
right. Then we had Unity Eyes, and they basically, in 2016, they published 1 million synthetic RGB images. And the tool, they also have, I think the tool to create the synthetic data is also public, but you'll have to check it out. And these are the kinds of results you got. It's not, I wouldn't say that it is photorealistic, but it's a start for sure, right? So you can see that the gaze is extremely real because it's all synthetic data, right? You know where this where the eyeball is located and how it is moving. And then we have NVGaze. This is NVIDIA in 2019. This is they have both synthetic and real images, 2 million synthetic near IR images. And the labels are gaze direction, eye location, pupil location, and region labels, right? Different regions of the eye, they have labeled also. And here you can see the dilation of the pupil. All this is synthetic, right? So the white of the eyes, they are, darker. The lighting is changed. They also have, you can see
Specularity there.
the specularity, the four that I was talking about. They have those kinds of things. And 2 million, that's a very big data set. So in addition to that, they also have 35 subjects and 2.5 million images from these subjects with various illumination changes, etc. So very, very nice data sets. In 2016, there was another technique called SimGAN that I found very interesting. what they did was they took, these synthetic data, it was being generated, people were getting a lot of synthetic data, but we all also knew that this synthetic data is not, it's not 100% realistic, right? It didn't look as good. We knew you could look at this data and know that this is synthetically generated. At that time, at least, that was the state of the art. So they came up with this very interesting technique that, okay, we have unlabeled. The important thing is that unlabeled, you did not say that this is, you didn't have to mark anything, right? So you took unlabeled real images and used a GAN, right? For people who don't know GAN, it is a technique for creating new samples of anything, right? Let's say human faces. You trained a GAN using human faces. Now you could generate a new human face, which follows the distribution, but it is not one of those millions of images you use to train it. And I think if you go to this person does not exist, it will give you a sample from from this distribution every time you refresh the page, right? So similar technique using GANs was used to take the synthetic data and make it look very realistic using unlabeled real images, right? And so this is very interesting because you're using, first of all, synthetic data, which was you find in abundance. You're also using real data, and if you don't have to actually annotate the real data, that too can be pretty abundant, right? It is not as abundant as synthetic data, but if you don't have to label it, then it's quite good, right? Yeah, the effort required is much less. Now, let me go over a few real data sets. UT Multiview 2013, this is a collection of real data sets. There are 50 subjects and 8 camera views, 160 gaze directions. Here, the head is held steady, right? They basically put the head in a chin rest, so the head doesn't move at all, and it's only the motion of the eyes, etc. So kind of contrived setup, but at that time, just getting that right was pretty good. The other assumption is that in a head-mounted display, the reference frame is connected to your head, and there is not much motion between the head and the head-mounted display. Still, very nice data set, right?
And just as a reminder to people, 2013 was over 10 years ago.
That's true. That's true. That's true.
I'm going to crumble into dust and blow away now.
Somehow, whenever this, the discussion about time and age comes along, I remember my son once told me, he's now 7 years old. He told me when he was 5 years old that his teacher is very, very old. And I said, how old is she? He said 40 years old. And I just, it broke my heart.
Hey, the kid wasn't lying. I feel it.
All right. So there's another data set called IDIAP 2014. And here they had 2 cameras, RGB camera and RGBD camera. 62,500 images, 94 sessions, 16 people total, 12 males, 4 females. But the interesting thing about this data set was that they had a 3D target. You can see that orange ball in some of these. So they were not just doing a plane, trying to detect where on the plane the person is looking at, but in 3D where this person is gazing, right? And that is why they had this Kinect system, right? They had this RGBD camera to locate the ball, and it's more than just plain gaze, right? We have the MPII Gaze 2015, very large data set, very popular data set, 213,659 RGB images, 15 people, and they were using this on everyday laptop, right? Use so that it is not a contrived setup. If you have a laptop-based system, right? If you want to find where the person is looking on at any laptop, you can use this data set for training your system. And the laptop and the screen were calibrated. The user was shown a pattern every 10 minutes. So they would do the regular work, and then every 10 minutes they would be asked to see a pattern. And so it does mean that when the data was collected at the time, they were not doing the normal work, right? Because they are looking at a particular pattern, but it does guarantee that you're getting people in many different environments, many different working conditions, etc. So that's a very useful data set. Interesting one in 2016 was gaze capture, and they just used Amazon Mechanical Turk, and they basically created a very large data set, 2.5 million RGB images of 1,474 people. If you look at other data sets, they are talking about 35 people, 50 people, that kind of. These guys, they really used Amazon Mechanical Turk and an iPad to create a very, very large data set. It's an interesting paper. You should go and read it because they talk about many different techniques to make sure that people are not cheating, right? Because these people, frankly, are not. I mean, they are motivated by making money, right? So it is very easy for people at the scale to have at least a fraction of these people who are cheating, right? And to make sure that they don't cheat, they had many different, user interface was very good. For example, when they asked you to look at something, they just didn't show a little dot. They would show something that is pulsating. And after you said that, okay, you have gazed at that, there was also a little letter L or R right next to that target, and you had to press left or right, right, based on what letter you noticed there. And if you did not notice, do it correctly, you'll have to do it again, right? So that way, they were ensuring that people were not cheating on this large project.
Unless they were just a very, very lucky guesser.
Yeah, 100% of the right, 100% of the time if they are right. So RT-Gene is another data set. This is interesting because even though the number of subjects is small, this is, the training images is also small, but they go for extreme head pose. And they have this very interesting gear. I think I included it just because I found the gear very interesting. So you remember that in the previous data set, sometimes the head pose, they wanted to keep it constant. If they don't keep it constant, then it's very difficult to know what the head pose was. But in RT-Gene data set, they wanted to get the head pose also without actually constraining the head. And what they did was they asked people to wear these glasses, and the glasses were taking the pictures of the eye. But these glasses also had this mocap system. You can see these three coordinates. You may be able to see these three balls. They are basically three coordinates, of the system, which was attached to these glasses. And then there was a mocap system, a motion capture system that people use in the movie industry to find these dots, right? And once these things are located from multiple cameras, they are, these, you can find the 3D orientation of the glasses with respect to the mocap system, right? That way you have head orientation because, you can assume that the head is rigidly connected to the glasses, and you have eye tracking, etc. So interesting. I found this very interesting data set collection procedure. So this is what it looked like, complicated system, but a very interesting system. You have motion capture, you have RGBD camera, you have eye tracking, etc. And one other thing that they did was at that time, the results didn't look very good, but I think now if you did the same thing, the results would look very good. They didn't want these people wearing glasses to be in the data set, because sometimes you may want this without the glasses. And they used a GAN-based in-painting method for removing the glasses. The results here, as you can see on the screen, they look okay, but with current methods, if you did this in-painting, it would be spectacular, right? You would not be able to see those little glitches that you can see. For example, in this image, you can almost see it doesn't look very good. So
Sort of looks like a Star Trek character with
right,
the ridged eyebrows. Like,
right. So yeah, so this is another capture method. OpenEDS is very interesting. This is, again, a virtual reality. This is for head-mounted displays, 152 participants, and they have semantic segmentation for every image. So here, for example, the various parts of the eyes, they have been located using semantic segmentation, not just curves, which, it shows better accuracy because, when you're using curves, etc., even though you say that this is an ellipse, it may not be exactly an ellipse. If you do semantic segmentation, you can exactly carve out the contours and show how it is, right? So, and in addition to that, they also have a very large data set of unlabeled data set. And that is also very good, because they could do whatever budget they had for annotation, but the rest of the data, collecting data is easy, annotating it is much harder. So, but unlabeled data can also play a role in improving accuracy, as we saw in one of the examples, right? So it's good that they gave this out. And in addition to that, they also have this point cloud of eye topology for 142 subjects. So they had this point cloud of eye topology that they got for each subject, which I felt that it could be very useful in solving the problem. So algorithmic trends, how are we doing with time?
we're about 7 over right now.
Okay, should we do the
Yeah, let's do our giveaway. Give
and
if
then
people
we'll
have
go.
to bounce off, then we can continue with this very informative and interesting presentation.
All right. Should I
Yeah, go ahead and
unshare?
unshare and we'll, yep.
Okay.
Howdy out there, folks. Thanks for sticking with us. It's really exciting to see the sheer number of you with us today. We've been over 300 concurrent viewers for the whole episode. We really do appreciate that. And so we're going to give something back to you in the audience. The very first person to answer the trivia question I'm about to ask will win the OpenCV course of their choosing. Only people in Zoom can answer this. Please just use the chat system to type your answer, and please wait until I've finished asking the question. If you have won in the last couple of months, please do not answer and give someone else a chance to get the free course. You can see what courses are available by going to opencv.org/university. And even if you don't win, invest in yourself, invest in your education, maybe upskill or get a new job. So, at the beginning of this webinar, we talked about the number of cameras on the Apple Vision Pro. There's 12 cameras. How many was Satya able to find just by looking around on the device itself? Ooh, all right, let's see here. Pamudu is the first one to answer. Oh, no, that's incorrect, sorry. Stian Hegna. The answer we were looking for there was 8. 8 was the one number that Satya was able to find. Stian, please send exactly 1 email to phil@opencv.org with the course you would like, and we'll make sure that the courses support team, who are awesome, by the way, will unlock that for you in your courses account.
Congratulations.
Congratulations. Somebody
right.
had some very amusing answers here. I think some people got frustrated that they lost. Someone said 32. It's a little too many. I was expecting.
Oh, that's off by 10. 42
exactly.
was the right answer.
Right. I was expecting the Douglas Adams reference, and I was let down there. The answer to life, the universe, and everything is, of course, 42. Shall we continue, Satya?
Yes. So let's go over the algorithmic trends, right? What are people using now? Where are things headed? So one of the things is that, all these methods that we have focused on, or we have discussed here, they focus on just one image. But is it not possible to get better results if we use motion data, right? Head motion data, not just one frame, but several frames to get better accuracy, right? And that is one of the trends. And the way it works is, there is, let me break this down, this complex neural network, into simpler parts so that it is easier to understand. So just imagine that you have this picture, right? You have one frame, and from that frame, you first detect the face, and then you detect the eyes, and you detect the facial features, right? So this becomes a feature vector. All this information, you put it in a feature vector. There is a problem, right? I mean, you may think that, can I not just detect the eyes to estimate the gaze detection? And here's the thing called Wollaston's effect, right? What it does is, this was, I think, by some artist who had created this optical illusion. Can you tell me where I mean, just imagine, you cannot tell me obviously, but just imagine where the person is looking at. You may be very confident that they are looking at, if you knew just that, if you just saw the eyes, you would be able to detect where people are looking, right? You may feel that, yes, it's very reasonable. I know where this person is looking, right? But what this artist did was, oops, okay. What this artist did was they changed. The eyes are not changed at all. You can see the eyes remain the same, and you change the person, right? The orientation of the person, and it gives a completely different viewpoint, right? The eyes are looking exactly the same. That is why, pose estimation, gaze estimation, it needs to have the head estimation also, right? You cannot just look at the eyes and say where the person is looking at if you don't know the location of the head. And that is why it is important to have the location of the head as well, right?
It's also really interesting to see just how old some of these problems are and how long people have been working on them and noticing them.
Right, right. Yeah, and I don't even know how old that effect was discovered, right?
I'll have to look it up.
So now, basically, you take all this information and then you run it through a convolutional bank of convolutional layers. And what it does is that, whenever you see these banks of convolutional layers, people are intimidated. Oh, what's going on? What are they doing? Why are there so many convolutional layers? Just think of them as black boxes, which are extracting essential features that are useful for the task that you're interested in. And they're just creating a vector. From an image, you're getting a vector, right? And what's happening inside, it's not important. Just imagine that it is extracting essential features and creating a vector of numbers, which will be useful for solving the task, which is downstream, right? So you again take the eyes, you run them through these bank of convolutional layers, and then you create a vector. And these are followed by these fully connected layers. At the same you do with features, and then you basically concatenate all this information. You add all these, you get these vectors, you just concatenate the vectors, and then you have some fully connected layers. This is very common in convolutional neural networks, that the things that you're interested in, you just create vectors out of them, right? An image, patch of an image or something, you create a vector out of it by running them through convolutional layers, a bank of convolutional layers. And once you get this information, you just concatenate them, right? The top part has the face, the middle part has the eyes, and the lower part has these features, right? And funnily, right, this information concatenated, it just works to incorporate all the information in these three different types of things, right? And whenever we have, when we have this time series data, right? When we have something in temporal domain, we use something called recurrent neural network. It allows you to fuse information across time, right? I cannot go into that detail right now, but that's what people do. And that's why you see this architecture where you have convolutional layers, and then you have for concatenating, for using information across frames, you use recurrent neural network, right? And then you have this final temporal prediction based on the time data as well as the spatial data. So just to summarize, right? And that last, I chose that last example. There are many different algorithms. I chose that example because it pretty much encapsulates a lot of different things that are necessary to make things happen, right? To make things good. That is why I chose that specific example. It's not that that method is the state of the art, may not be the state of the art right now, but it just gives you an idea of where things are moving, okay? So just to summarize, there is a push towards large synthetic data. We also are looking at very specific application-specific data sets now. And there is a push towards crowdsourcing and automatic annotation for real data. Things are getting sensor heavy for real ground truth annotation. As you can see that, in that one example, we saw mocap information being used for head pose estimation. So a lot of sensors are being used, and this will continue. And now with, not only that, initially, a lot of people were just focused on the eyes, not the face, but now facial features will also be used in determining the location of the eyes, full face, full head, etc. And then there will be push towards using temporal data. So it's not done on a per image basis, but on, a few frames at a time. So that's pretty much what I wanted to cover in this talk. Happy to take any questions you have.
Awesome. Thanks so much, Satya. Andrew Fenton in the chat mentions the Wollaston work was 200 years ago.
Wow.
1824, 200 years ago this year. Holy cow. That is bananas. Absolutely bananas. There were quite a few questions here, but you pretty much answered all of them. If anyone wants to chime in there and ask any last minute questions, we definitely have time. We'll have time for one. Before we get to that, though, I just want to, if you come up with something later, or maybe you're watching this in the recorded version and you have a question, there's a bunch of different ways you can ask us, and we'll do our best to answer them off the show. If we didn't get to your question, please ask us on social media. Send us a message on Mastodon, Blue Sky, LinkedIn, or Twitter. We're on all of those channels, and I'm going to go ahead and post the links in chat here. And of course, this episode, the recording of this episode will be available on our YouTube channel. That's at OpenCV Official on YouTube. I think we're about to pass 17K subscribers on that. So thanks so much, everybody, for that. Let me just briefly... we've got some other OpenCV business to discuss here at the end. While we're watching the questions here, Satya, do you want to talk a little bit about how we're opening up the development of OpenCV 5?
Yeah. So
I'm going to go ahead and share my screen. I'll put the GitHub up here.
Right. So as you know that we raised we had a Indiegogo campaign for OpenCV 5, and the development process has started. And just to have more transparency on how we are doing things, we decided to have your screen is shared.
Yeah. What is it doing here?
So
Sorry about that.
we are putting the project, we are using the right project management tool inside GitHub to publish, right? What are the things that are being worked on? What are the things that are on the ice right now? And who's working on what? All this information is public. So these are the current tasks that are on the list. Some of the things that you may recognize, we are having. It's slightly difficult to understand all the little details because they are very technical. For example, the last one here shows DNN cleanup, which is on-fly quantization removal. So some of these things, we have discovered some things work better than the others. Some things are useful for making things faster. A big change in OpenCV 5 is going to be removal of the C API. And so you can see some work that is being done there. There will be new things for hardware acceleration layer. A lot of old algorithms will be pushed out to OpenCV contrib. So you can see at the bottom there, move ML to OpenCV contrib. But so machine learning, so the OpenCV had a bunch of machine learning algorithms that will be, moved to OpenCV contrib. Other things like HOG, pedestrian detection, the regular HAR-based face detection, etc. They are also moving to OpenCV contrib because, frankly, they are no longer the state of the art, right? We have much better face detection inside OpenCV, right? So we didn't want people to get confused that, should be using HAR. There is,
Makes
for
sense.
example, UNet, which does face detection, etc. So
Mhm.
yeah, this thing is, you can go and check out this. This is a public project thing, which we will
Mhm.
keep updating. Some of it is automatically updated, but we'll keep updating. There is another announcement somewhere. Phil, do
Mhm.
you remember?
Which one?
uh, no, another announcement on this, right? When we make some progress, are we going to send information through our newsletter or?
Yes.
Okay.
Yes, definitely.
Okay. So every month we are going to publish a blog post and also share that using our newsletter on what is the progress we have made on OpenCV 5.
Yep, and you can also do this is a public workboard here on GitHub. I posted the link in chat there. You can just go to the OpenCV org and you'll see the project there. This will include all of the OpenCV, OpenCV contrib, OpenCV Python will all be on this workboard here. And yes, the best way to stay up to date is to follow the OpenCV blog at opencv.org and subscribe to the newsletter, of course. We've got a few other things to discuss here I want to make sure people are aware of. One is OpenCV is looking for volunteers still. If you have time to donate, if maybe you're a student or maybe you're just a professional that uses OpenCV and wants to give back to the community, you can fill out this form here and volunteer your time. We're still figuring out the best way to utilize OpenCV volunteers, but we really do appreciate the enthusiasm. We've actually had over 300 people sign out the volunteer form, and I am very behind in reviewing those applications. So we'll take a look. Hopefully this week we can catch up. There's also the OpenCV Cool
Do
Stuff
we need a
submission
volunteer
form.
to review the volunteer application?
Yes, I think that might be the first task. I think good call, boss. That's why you make the big bucks. We've also got the OpenCV Cool Project Forum. OpenCV Community Friday has been going on for the last 11 weeks, which is when we share cool projects from the community that people have posted on LinkedIn, Twitter, Facebook, et cetera. But there's also a direct form here that you can send it to us. If you've got something that you made recently or even just saw online that you think would be interesting to the community, we will consider that for inclusion in the Community Friday newsletter. So check that out. OpenCV has an official shop now, a merchandise store for the first time ever. We've got several different t-shirt designs and a bunch of different, not just t-shirts, but a bunch of different other stuff. There's tote bags, pins, stickers, pet bandanas, which please, if you buy one of those, take a picture of your dog in it. We want to see that. We've also got 3 different flavors of the I Love OpenCV shirt. We've got English, simplified Chinese, and an Espanol. So check those out. Bunches of different colors, bunches of different styles. We tried to go as broadly as possible to make sure that people get something to rep OpenCV if that is in fact what they want to do. There's also other ways to support OpenCV. For example, you can directly give us money via either PayPal or Stripe now, which is something that is pretty new. A lot of people were asking during the campaign for OpenCV 5 if there was some way they could donate off of Indiegogo or off of the crowdfund platform. And so now we've implemented that. You can use a credit card, you can use PayPal, whatever. If you're part of an organization that utilizes OpenCV and you want to directly support us, you can donate either financial resources or potentially developer time to help us out from some people on your team. We have 3 different tiers of that. You can find all this information by going to opencv.org/support. We also have sponsorships open on GitHub. If you want to use that platform, you can click over here and see $9 a month on GitHub, and that goes into the development of OpenCV. So yeah, that's all I got for right now.
All right. Thank you so much.
Yeah, I think let's wrap it up. Put a bow on this. You ready to take us home, boss?
Yeah, so I'm very excited with these new devices, etc. Right? I mean, things that were in research domain just a few years back, they are now in real products and they are performing exceptionally well. Like I like to say that we are living in the future, right? So please stay connected. I'm very excited about this new device. In fact, we will have another session on Apple Vision Pro. We are getting some experts who have bought Apple Vision Pro, and just the number of vision features on this is just amazing. Eye tracking is just one of them. The bigger one is tracking of the headset with respect to the environment,
The room
which
scale
uses SLAM,
tracking.
etc. So it is that, that requires some of the cameras. Then we also have hand tracking, as well as hand gesture tracking, which works exceptionally well. So this device is loaded with those features. And on 29th, we will have a discussion of some experts who have bought this thing and they have been trying. It's going to be very interesting. So I'll be one of them, but we will also get other people. Still, the list is being decided, but it is going to be a fascinating session as well. So,
yes, and you'll see some familiar faces. Next week, we've got Team Optus Sentinel, the popular vote winners of OpenCV AI Competition 2023. And then the week after that will be the Apple Vision Pro roundtable discussion.
That's great. So thank you, everybody. Thank you, Phil, for organizing the show. And I really, really appreciate all of you coming and spending time with us. Hopefully this session was useful, informative, and we'll do more of these, when we get these empty slots.
Absolutely. Happy belated Valentine's Day to all you lovers out there. Te amo, mamacita. Take care of yourselves, take care of somebody else if you can, and have a great day wherever you may be.